Welcome to Easy Alim Learning Simplified. My name is Ruth, and today we are going to be looking at the topic chlorine and its compounds. So we are going to look at some of the other properties of chlorine that is going to help us to conclude the topic on chlorine so that we can move to hydrogen chloride. So initially we talked about how chlorine was reacting with metals and nonmetals, but today we are going to focus on the oxidizing properties of chlorine. So chlorine is a strong oxidizing agent, so it oxidizes many ions by really accepting electrons. So if we talk about it being an oxidizing agent, it means it undergoes the reaction of reduction. Reduction means it gains electrons or loss of oxygen. In this case, since we are not talking about oxygen, we will be talking mainly about gaining of electrons, which is a definition you learn later on in Form 4. So that's the reason why it accepts electrons from the oxidizing agent. So during the process, chlorine itself undergoes reduction, as we have said the process. So for example, if chlorine reacts with hydrogen sulfide gas, so a gas jar full of chlorine is inverted into another jar containing hydrogen sulfide. So that's what you see in the reaction. So we have chlorine, we have hydrogen sulfide that are going to react in that jar. So one of the things you notice is that there will be a yellow deposit, and we know definitely this yellow deposit is because of the production of sulfur. And then we also have some misty fumes formed of hydrogen chloride. So this tells you that chlorine reacts with hydrogen sulfide. There is an interchange of ions to form hydrogen chloride and sulfur. So chlorine oxidizes hydrogen sulfide to sulfur, and then itself is reduced to hydrogen chloride gas. So you can see from the equation, chlorine reacts to form hydrogen chloride, and then hydrogen sulfide reacts to form sulfur. So chlorine is undergoing through reduction, so it's an oxidizing agent, and then hydrogen sulfide is undergoing oxidation, so it's a reducing agent. So this also reminds us of some of the reactions of hydrogen sulfide as we looked in the previous lessons. So one of the gases must be moist for this reaction to occur, otherwise it's not going to react to occur. In absence of moisture, both gases are still in molecular form and hence cannot react. So we need the water to facilitate the ionization, which gives them now the ability to react. So if aqueous hydrogen sulfide is used, the sulfur forms a yellow suspension on the acidic solution. So chlorine reacts with hydrogen sulfide, form hydrochloric acid and sulfur. So the chlorine gas reacts with the sulfide ions to form chloride ions and sulfur. So you can see chlorine is going to lose some electrons, and then sulfide is going to gain those electrons. So it can also react with sodium sulfide. So when chlorine gas is bubbled through sodium sulfide, so the resulting solution is divided into two portions. So the first portion we add dilute nitric acid, and then followed by barium nitrate solution. And then the second portion we add the 2 nitrate, and then we warm. Pay close attention to these reactions. So when we take chlorine and bubble it to sodium sulfide, and then we add dilute nitric acid followed by barium nitrate. So the first portion, there's a white precipitate that is formed due to the presence of sulfate. So we start with sulfite ions. So the chlorine gas must have oxidized the sulfite ions to sulfate. And then there's dilute nitric acid that is added, followed by barium nitrate. So it means that the barium ions react with the sulfate part of the insolution to form barium sulfate. So the white precipitates usually indicate the presence of sulfate ions. So as we said, chlorine oxidizes the sulfite ions to sulfate, and then itself is reduced to chloride ions. So water plus chlorine plus sodium sulfide forms sodium sulfate and hydrochloric acid in the first reaction where we add chlorine to sodium sulfate, don't forget. And then now it means now in the ionic sense of it, you can see the sulfite ions are being oxidized to sulfate, and then you can see the chlorine ions are reduced to chloride ions. So if we add barium nitrate in this solution, the barium ions will react with the sulfate ions. Remember in sodium sulfate, let's not forget. So it forms barium sulfate, which is a white precipitate. So the solution is first acidified with nitric ions before adding barium nitrate to prevent precipitation. We do not want the barium sulfite to precipitate. Because you know that if we had the sulfite and carbonate, then the acid is going to interfere with that reaction because it's not supposed to form a white precipitate. But because now we have added acidified, or we have added the acid, it prevents now that precipitation of the sulfate and carbonate. So if there's any sulfite ions present, they are going to dissolve. So that helps it to just remain as sulfate ions. I hope you've understood that part. And then to the second portion, remember we added the lead nitrate ions. So, and then we warmed the mixture and the white precipitate dissolves and then recrystallizes back on cooling. So first of all, the white precipitate shows the presence of the chloride, sulfate, and sulfite. Remember this one we did not acidify. Make sure you are noting that part of the acidified. So if you use the acidified barium nitrate or acidified barium chloride, we are eliminating the presence of sulfite and carbonate because those ones would definitely dissolve. But in the second reaction, we only just added the nitrate ions in the solution. So it means the lead ions can react with the sulfate ions and chloride ions and sulfite ions in the solution. But when we warm, if we warm and the white precipitate dissolves, it tells us it's a chloride because you know that lead ions or lead chloride usually are in white precipitate, but the precipitate dissolves on warming. So that confirms that it's chloride ions and it's not sulfate and sulfite. Please note that. I repeat again. So the first step, when chlorine reacts with the sodium sulfite, that reaction occurs to form sodium sulfate and hydrochloric acid, right? And then we added lead nitrate ions. So when we put this lead nitrate, the lead ions in solution react with the chloride ions in hydrochloric acid. It can also react with the sulfate ions in sodium sulfate. That's why our conclusion can be in the first inference will be presence of chloride ions, sulfite ions, and sulfate. It can be either of those. We have not confirmed. Remember also because there is no acid, we can comfortably say there is sulfite ions. But now the moment we warm the solution and the white precipitate dissolves, it helps us to confirm that indeed it was chloride ions that we are working with. Because it is lead chloride that dissolves on warming. So make sure you're able to see that process clearly and you see how the acids and the nitrates are being used intentionally to help us eliminate. So the lead ions react with the chloride ions to form lead chloride, which is a white precipitate that dissolves on warming. So chlorine also reacts with ammonia. So if chlorine is bubbled in ammonia, you're going to see some white fumes. The white fumes are because chlorine gas oxidizes ammonia to nitrogen and then itself is reduced to white fumes of ammonium chloride. So you can see this is the reaction. Ammonia reacts with chlorine to form ammonium chloride and nitrogen gas is given off. Also, chlorine undergoes some displacement reaction with other halogens. So if you bubbled chlorine in solution containing fluorine, bromide, iodide ions in separate test tubes, you're going to see some observations. But first, if you look at the first with the fluoride ion, since fluorine in the periodic table is higher than chlorine, it means there's no way chlorine can displace it in solution. So that's the reason why there's no observable change that is seen in this reaction, because it's a weaker oxidizing agent than fluorine. But with bromide, if we were using potassium bromide, then the colorless solution turns red brown. The reason why it turns red brown is because chlorine has a higher tendency to gain electrons, so it oxidizes the bromide ions to form potassium bromide, from potassium bromide to potassium chloride, and then bromine, which is given off, dissolves to form the red brown. So if you were to look at the equation, you can see the potassium bromide reacts with chlorine. There is an interchange of ions because the chlorine has a higher tendency of gaining electrons. So it forms potassium chloride, and then bromine is given off as the red brown gas. And then with the iodide ions, this reaction also is going to occur because chlorine is higher than iodine in the reactivity series. So if we were to use the chlorine in potassium iodide, it will form a black solid would be deposited because chlorine will have a higher tendency to gain electrons than iodine. So it oxidizes the iodide ions to iodine and then forms chloride ions. So the iodine solid in the resulting solution makes it black. So you can see it can do that displacement. So when you react potassium chloride with chlorine, it will form potassium iodide with chlorine, you form potassium chloride with iodine. Liquid is given off. So it also reacts with alkalis. For example, chlorine can react with sodium hydroxide solution. So in this case, it is important you note the temperatures of this sodium hydroxide. If it's a cold sodium hydroxide solution, you notice that the paper is going to be bleached because this reaction forms a bleaching agent. So chlorine dissolves in sodium hydroxide to form sodium hypochlorite. The sodium hypochlorite bleaches because it gives out that oxide, that nascent oxygen to the dye. So you can see the product that is being formed is sodium hypochlorite, and this is in the case where it is cold and dilute. So that is the equation. If it's concentrated, hot and concentrated, you can see it's forming sodium chloride 3, which is a bit different. This is still a bleaching agent, but you can see this one how it bleaches. This one dissociates to give a colorless matter. It also reacts with calcium hydroxide to form calcium hypochlorite or calcium chloride 1. This is what we refer as the bleaching powder. You have had the assessments where you've been told to identify bleaching powders. This is a bleaching powder when calcium reacts with calcium hydroxide reacts with chlorine. It smells strongly of chlorine because it reacts with carbon dioxide in the air to form chlorine. So when you react calcium hypochlorite or calcium chlorate 1 with chlorine, you form calcium carbonate and chlorine gas is given off. Finally, let's look at some uses of chlorine gas and its compounds. So chlorine is used in the manufacture of hydrochloric acid, as you see in the next lesson. It is used as a bleaching powder. You can see it formed the calcium chlorate 1. And then in paper industries, it is used also for sterilization of water for domestic and industrial use. Especially, you've seen it being used in swimming pools. It's also used in the sewage treatment, especially this sodium chloride 3. It is used in the manufacture of plastics as well, especially the PVC. We'll learn about the PVC later in Organic 2. It is used in the manufacture of germicides or pesticides. And then the CFCs are used in the manufacture of aerosol propellants. But this also has an environmental impact on the environment. It's used in the manufacture of chlorofluorocarbons, and chlorofluorocarbons are used as refrigerant as well. It's also used in the manufacture of chloroform. So that brings us to the end. We know chlorine has its own advanced effects. You'll notice these advanced effects later in the environment. When you talk about plastics and chlorofluorocarbons, you talk about them again when you're talking about organic chemistry. So you notice some of these things in terms of pollution. You also notice them in other topics. So that's it. In the next lesson, we're going to look at hydrochloric acid and how it's produced in the laboratory. So see you in the next lesson.